Well, thank you very much for this very nice introduction. I'm really, really happy to be here today and explaining you what I've been working on the last couple of years, and especially to introduce our team. This is the very, very first time that we're introducing our team, RoboCup at Home, and one of our members is actually in the audience. So Patrick, identify yourself. Yes, so you can go, of course, to our booth, and then you can experience what we have been working on the robot. This is a very nice student initiative, and I will talk about at the end of the presentation about this. If you have any questions, you can, I don't know if they can interrupt me or we'll leave it till the end. I try to make it as interactive as possible so they don't fall asleep, and we try to always be in track. So my name is Karinne Ramirez. Today I'm talking about my research, which is mainly on robotics, and which is for artificial intelligence. This is our team, so I'm very lucky to be part of this Institute for Cognitive Systems. Like you can see here, if you count the number of humans compared with number of robots, robots are winning now, at least in our lab. So we have different kinds of robots. So this is the robot we brought today. This is Tiago robot. This is from a Spanish company. And this is the big brother of Tiago. This is a bipedal humanoid robot, which is a bit more complicated to transport, but you are welcome to come to our lab and we can show you. We have the iCup, we have the Pepper robot, we have our own custom-made mobile-based manipulator, which characteristics is that we have artificial skin, developed also in our institute. We have another service robot, which is PR2. And we are building also some humanoid robots with low cost. This is one of our more updated pictures, but not everybody was already in the picture, so some of our colleagues are missing here. And this is so that you can see only the robots. So we have a lot of robots, even hands. Here, for example, you can see this is Allegro hand, which is a really nice robot. We have industrial robots like the Mitsubishi or the Universal robot. So we have different kinds of robots. And then our institute also works in different levels. So we have the social interactions, we have the low-level controllers, we have the human-robot interaction, we have building of sensors, and we have perception systems, we have reasoning systems, and today I will talk about what we are doing in the reasoning side. So, what do we expect from robots? Maybe some of you are familiar with this cartoon, I hope so, because otherwise I'm very old. This is Rosie, right? So the Rosie robot is expected to know what the human is doing and then react to this command so that he can better serve the humans, right? And then this is the ultimate goal. So we want to achieve and we want to help the elderly people. So the idea is that they just take it out of the box, right? They just push a button and then the robot is doing everything he knows and the lady is just giving the groom, right? If the lady just gives us the groom to us, we already know that he wants us to clean, right? And that's the interesting part here. How is the robot knowing that he needs to start cleaning, right? And then what can we do with the robots so that the robots can actually learn really fast and very intuitive such that also people that are not roboticists can actually interact and learn, right? Another really nice, I'll just put it back because yes. Another really nice movie, I'm pretty sure we are familiar with this, the AI movie. So in artificial intelligence, this is the David robot and he just arrived home. But just look at, he's just observing the behavior of the parents, and then he's imitating, right? So he's adapting to his new environment, he's learning new activities on demand, and then he's observing also the other person, and then he's trying to imitate. So a lot of things are happening here. So he's observing, he's interpreting, and he's executing. And this is the goal, right? So the goal is that the robot right now, for example, of course, you are in Germany, and we want our robot to pour our beer, and we cut our sausages, right? So he just see the pictures here, could be a video, could be a recipe, could be a normal plain instructions, and then he sees on his table the same ingredients, and he wants to achieve from what he's observing to actually execute the activities. So for this, he needs to observe, interpret, and execute the correct primitives so that he can achieve the similar behavior. And this is going to take us to a more flexible robotic system so that we can also generalize to real-life situations. And then the problem is when we have robots, maybe in the picture you saw that I showed before, that we have different sensors, and different robots have different sensors. For example, imagine that you have a kitchen, and then you have with a lot of cameras on the kitchen, and then you will have something like this kind of view, right? But then imagine most of you are now trying the HoloLens, right? And the HoloLens is really cool because then you have the environment information, but then the problem is you have everything. So the system needs to define what is important, what is not important. And depends on what kind of input information the robot has, then he needs to try to adapt to this information and try to recognize this information as soon as possible. The problem is, when we're talking about perception system or perceiving the environment, is like, depending on what kind of input sensor is the type of properties that we can extract, right? For example, if we have videos here, we can extract the color of the objects, okay? We could also have recipes from the internet, and we can do the mapping between what we are seeing in the internet and what I have in my environment. Or nowadays we have the GoPro cameras, and with this we can actually see our egocentric view, our first perspective. And this is very interesting because this is the view that robots has, right? They always see it from the egocentric point of view. And virtual environments, of course. From virtual environments, then we have everything, as I said before. Then the problem is, what happens when our robot has more than one sensor? Can we actually combine all these different technologies into a common framework such that we can reuse everything? Or we have to implement just for the virtual reality, and then I implement for the color base, for the video cameras, etc. And this is what I've been working on right now. How, if the robot has different sensors, how can we create a common platform so that he can observe, understand, and execute? And more importantly, we can transfer to different robots, because as you saw in the lab, we have different robots, and we don't want to start programming each robot each time. So in this presentation, you will see different robots being programmed, learning from execution. And the main task is to understand human activities. And then you will say, come on, how complicated it is to observe a human? Well, humans, we are really very complicated. We have several different ways of performing exactly the same task. In this case, we asked the participants, random participants, we told them, okay, here you have the ingredients, now you have to do a sandwich. And for that, all of them executed as a first task, cutting the bread. But then observe the first one, this is a behavior that we will expect, right? Normally cutting the bread. But then observe the second participant, for some reason, I still don't understand today, she decides to roll the bread. I don't understand why, but she did it, right? And then on the last part is left-handed person, which we actually have these situations, right? So then how can we define a system such that we can only train these because we have only seen these once, and then on real-life situations, we can see this kind of behavior or this kind of behavior, right? And this is the goal. We have different styles, we are different people, and we have to adapt, okay? And this is what we have implemented right now. So we have different input sensors like camera, videos, trajectories, virtual environments, and we have also kinesthetic teaching. And what we have developed is a perception module that is actually extracting information depending on what kind of input data you have. Trajectories or features, or like you will see on the demo right now, we have deep learning algorithms, virtual environments, we have kinesthetic teaching, and this is coming into our semantic reasoning engine to create the meaningful of the tasks. After that, we are enhancing our generation of the semantics with the knowledge representation, and then this is going to command the robot what to do. Okay, and in this case, we have integrated this system in the ICOP robot, the Heinz robot, and Tom robot. And as you see here, this gray area, we call it robot agnostic because it can be transferred to different robots without doing anything. Okay? And this is what it happens. So what we are, the problem we are facing is that we always live in the continuous domain. Okay? And then the problem is that we need to discretize, we need to create symbolic representations because we humans are connected in a symbolic representation into a really high level representation, right? But then what happens if you segmented trajectories for the same activity? Imagine that, I have bottle. So imagine that I have the bottle and I just move it like here, right? But then I move it on the front, and then I move it on the back. And all these different positions will generate different trajectories, right? Different velocity trajectories, different distance trajectories. And what we did is that on top of these trajectories, we combine it with a reasoning engine so that all these trajectories, even though a k-means algorithm will tell us, okay, you have 3 different behaviors, it's not correct because we only have one behavior. Different demonstrations, but it's actually one behavior. And this is possible because we have different abstraction layers. So the lowest abstraction layer is actually what we robots can observe. Like, for example, it's very simple. You can actually tell me if I'm moving or not moving my arm, right? Moving or not moving is a simple thresholding of the velocity. But only moving the arm is not enough to understand that I'm actually reaching towards the object, right? So for that, I need the contextual information, which is with the object properties. So we have in this case 2, like I'm getting closer to the object, which is I'm acted on the object, or I have the object already on my hand, right? This is the second property. And with this information, our semantic reasoning engine, what it does is that he transforms these low-level parameters to a high-level representations that we humans can understand. So if I tell you, can you reach me can you reach the cola, or can you bring me the cola, or something like that, we understand these commands, right? How do we do that? So at the beginning, we have a supervised algorithm. So we have, for example, in this case, we have a video. And in this video, what we have is that we segment the motions of the person, so like if the person is moving or not moving, or acted on the bread, acted on the knife, etc. And with this information, we are going to create a decision tree algorithm, a C4-5 algorithm, and from this, we are going to obtain the semantic representations in if-then form, okay? We have 2 different approaches. So we have this approach, which is basically, we are going to train always on the sandwich making scenario. We are going to extract the symbolic representation from the lowest level. And then we are going to have our training phase to obtain the basic activities. And then we can also have granular activities. Then the interesting part comes. What happens that when I use in the system a totally new video, in this case, the pancake making, I don't want to do training again because I want the system to reuse his past experiences from making a sandwich. Therefore, I neglect this part and I just continue to the reasoning part and the semantics, the things that I extracted from previously learned behaviors. So can you imagine more or less what kind of size of tree we are going to have? Like massive 300 nodes, 5,000 nodes or something like that? Yes, maybe. So you will be surprised to know that this is the tree we found. It's a very simplistic tree. However, it's very powerful. For example, I can demonstrate you right now. If the robot is right now looking at me, he will know that I'm grasping the object. Why? Because my right hand is not moving, but I have something on my hand, so I'm taking the object, right? Even though I didn't train it with bottles, our system can actually tell me I'm taking the object, and now I'm just putting the object back to this stand, right? And this is the rule here. Then the key point here is that we're using an ontology behind. So we are trying to make as general as possible all the objects, so that even though I didn't train with bottles, we can still reuse it because bottles are a subclass of objects, right? And then we have all these granular activities. What granular activity means is the activities that actually cannot be generalized as general as the basic ones. Like this, we call the pick and place activities. These ones, for example, imagine that this instead of the controller is a knife. Then you probably will not know what I will do with the knife, right? Most probably I will just place it on the stand, or maybe if I'm in the kitchen, I will put on the dishwasher, but maybe I will also cut. Right? And what is defined is behavior? Behavior is defined by the object I'm acted on, right? If the knife is being acted on the bread, that means I'm cutting, right? And that is also happening with the vegetables, for example, the cucumber or the carrots or something else, right? And this is very interesting because you will see now the system, we're always using this exact same video. And then we are using all the experiences and the reasoning that we obtained, and we tested in the pancake scenario video, We tested also with egocentric view videos. We tested with the setting the table videos and with virtual reality videos. For perception, we have two different kind of approaches. We have the offline approach and the online approach. So the offline approach, basically you need to train lots of samples. For example, for deep learning, you need a lot of samples. But you also can have online systems like the color-based system. Color-based is the simplest algorithm you can find in the literature, but it's very fast and it's a bit robust if you have the correct features to be extracted. This is what is happening with the deep learning algorithms. We have three different views from the same person doing the activity. Then we have two layers. So this is the independent subspace analysis, the algorithm. In this case, we obtain all the interesting features from the video, but not all the features are interesting. For example, I don't really care if the wall is behind and is white when I'm tracking the hand, right? So all these non-important features are eliminated, and I'm only using the important features here to cluster it into, I'm moving the hand, not moving the hand, I'm using a tool. And then this is a sample representation of what the network is doing, so it's sampling randomly. And this is coming into the input of the system, and then the output is this. We tested this on, of course, in benchmarks data set to try to see, okay, how good our system is. You can see this is a very popular data set, which is the Hollywood 2. And in this set, you have, for example, answering the phone. How complicated it is to detect answering the phone, right? But then the network cannot detect it really well. Then we say, okay, let's put our data set of the sandwich making scenario, and then this is the problem. We have 35% and 10%. Can you imagine a robot just detecting 10% of the time that you are reaching something? That is not possible. And then we say, okay, what happens when we include our reasoning system on top of this deep learning algorithm? And then we have overwhelming improvement, right? So we went from 25% to 81% by including the semantic reasoning part. This is just the representation of what is going to happen on the color-based system. We have different persons, different colors, and we have as well the same representation. And this is an example of how it looks in a live demo. So in this case, the system has been trained, of course, with this scenario. So it's expected that the system is recognizing correctly the activities, as you can see here. The activities are also detected, so for the right hand here, which is the one cutting. And then when the system finishes, you see that now the reasoning is also changing. Now, what happens when our system has a new video? This is exactly the same tree, if you saw the previous one. And the system is able to reuse everything that he knows. And now the interesting part is here. He has a new activity. Then the system recognizes that he has a new activity, and the user only has to tell him, okay, yes, this is a new activity, and then this you will call purring. Then you saw the system automatically generates the purring activity. Because we want to teach robots on demand new activities. We cannot program everything in advance, but we can enable the system to learn these things on demand. And then, as I said at the beginning, we can track both hands at the same time, but the hands are not doing the same thing at the same time, right? So in this case, we have that one hand is opening the bottle while the other hand is holding or is pouring while the other hand is doing nothing. And the accuracy is also quite good, like above 80%. And then the next task is, okay, I'm talking about robots, so what about putting this on a robot? And here we have the inference part, and the inference part, remember, has to be really fast, has to be very accurate, such that we can put it on the controller of the robot. First, we are going to test with the iCop robot, and here is an example of what is happening. So imagine that the robot is looking at the YouTube, and this window that you see here is everything that is happening in his brain, so everything that the robot is being processing. So the robot is extracting the features and then understanding what is the human teaching, and then now the robot is trying to execute the proper primitive, like, oh, okay, now I have to reach, right? But then observe that now the robot stops because he needs to go back to the video and see what is the next step he has to do, right? So in this case, he understood, okay, now the human is grasping, now I will grasp, right? And then the next task, put something somewhere. But it is also important that the robot can detect this very fast. This video has not speed up, but you will say, yeah, this is very slow. It's slow because the robot has not been speed up for security reasons. But the tech here, the recognition is happening in 0.12 seconds, so it's quite fast. And here you can even see that the human is not even purring, while the robot is already finishing the purring, right? So here we are getting closer into understanding what is the intentions of the human before the human is finishing the intentions. And then what happens when we have a different environment, a different input data, for example, virtual reality. To the virtual reality, then, as I said, we have everything, and now we have 3D data instead of 2D data from the cameras. Our robot can reuse everything that he learned from the making a sandwich. And this is the experiment that we run. So on this part, you can see this is the avatar robot in the virtual reality system working. And here you can see that now the robot is not always standing on the table. So now the robot is moving around, right? We have not trained this. And then our system is able to actually understand what the robot is doing, the intentions of the robot doing, his robot body here. And then he's now grasping the bottle. And then you see here, the avatar robot is moving towards the trash, but our iCup robot cannot walk. So he's observing that next to him is the trash. Of course, we put it there intentionally, of course. And then he's just throwing it away, right? So he's understanding what he needs to execute, and he tries to achieve as best as possible the execution. And this is a bit longer sequence. Then, at the beginning, I told you that we have different styles. And this is what I would like to show as a result. This is the person that you remember was rolling the bread, and this is the person that it was left-handed, and everything is based on what he learned from the pink participant, right? So in this case, you see the average is quite good, and then you may be wondering, yeah, but this is 25%. This is not good, right? The problem is that if you remember, we are using a color-based system. And notice that the objects sometimes get occluded with the bread, and they are always, look at this now, for example. They get transferred from one hand to the other. And that is a bit complicated to track from the perception side. But here you observe the pouring, and here you observe a new activity, which is actually the flipping activity for a pancake. Because at the end, we want our robot to make our pancakes. We have not yet succeeded, but... And this is what we say, okay, let's test our algorithm in our robot. And this is the other robot. So our robot is using the experiences from the iCup. And in this case, he's tracking both hands at the same time. And then he's executing what he's observing. One important fact that we have to consider here is that the robot, how does the robot know that he first needs to move the bread before cutting? Because if he doesn't move the bread and he just go and execute the cutting, he will just cut the table, right? How does he know that? Well, he knows that because you are demonstrating that, right? This is something that we innerly have, but we actually demonstrate, okay? And this is what the robot is actually also obtaining, is segmenting, recognizing, synchronizing, everything is happening at the same time. And then he finished the demonstration until the person is finishing demonstrating the task. And then what happens when, okay, I don't have a video, I don't have a virtual reality system, I only have the robot. And for example, if you have a KUKA robot, then you can enable the compliance behavior. And in this case, we have our mobile manipulator, which I mentioned before. We have our artificial skin. In this artificial skin, basically you have proximity sensor, temperature sensor, gyroscope, and LEDs. And then you can just move the robot and you will have a compliance behavior. So in this case, our robot, this is our robot Tom. Tom is having all the experiences from the previous robot, so he knows how to make a pancake, he knows how to make a sandwich, and now we have an industrial setting. In this industrial setting, we don't expect to have a person demonstrating in a video. Most likely, we'll have the user that is actually manipulating the robot. And here, you don't see them, but we have cameras here on the head of the robot. This is the output of the cameras. And this here is actually the recognition of the robot at real time, right? So the human just need to worry about demonstrating, moving the robot, and then the robot itself is going to learn everything, right? So in this case, the human is teaching how to sort oranges. When you go to the supermarket, probably you will not grasp the first orange you see, right? You have it, you test it, and you say, oh, yeah, this is a bit stiff, this is a bit, now it's good for eating, and this is what the human is teaching the robot, how to sort oranges and what to do with good oranges and bad oranges. In this case, he is going to teach that this is an activity for recognizing good oranges. He needs to go to this squishing area, and he needs to do the squishing. And then here you will see all the activities that the robot interpret while the human was demonstrating. So the user just needs to say, okay, yeah, I want this, save, right? So this is what we are trying to do it as intuitive as possible so everybody can program a robot. And in this case, the human is saying, okay, I teach you how to recognize the squishing, and now I will teach you where to put the good orange. So the good orange will go to the box to be packed, because this is an industrial setting. We have a conveyor layer, for example. And when it's not a good orange, it's going to be to the trash, maybe for juice. And then the user just say, okay, now I teach you the whole process. Now you have to execute the process. And if you remember, when we were teaching, we only have one orange. In this case, we have multiple oranges, right? And you see, the robot is actually testing. Of course, this is a bit speed up, 4K. I was just looking at the other presentation from the cars, and they actually slow down, and for robots, we speed up. So in this case, the first orange, I think it was a bad one, and then the second orange is a good one, and then he's going to recognize. So this is for an industrial setting, and in industrial scenarios, the user have different objects, and these objects are happening and changing very constantly. Imagine that now the producer has apples, and he wants to execute this exact same procedure. So the robot understands that he is reasoner and says, okay, this is an apple. I'm not supposed to squish apples. If I squish an apple, I will destroy the apple. So if you see here, the robot skips the squishing part, and he is just packing that. And this is all possible because of the reasoning that we have behind, right? So in this case, yes? Yes, yeah, so in this case we have an ontology, and in the ontology he has it's an apple, and he has not squishable property.
So he knows properties, the difference
yes.
between oranges and apples.
For example, yes. The interesting part here is that the robot itself is the same process, so the user didn't have to program the robot anymore, so we provide the ontology, we provide everything, and then the robot just adapts. Exactly, for example. We are working right now on how to include new elements in the ontology, yes. But this is our proof of concept of how powerful having a reasoner behind is. And then we say, okay, let's move to a totally different domain, and then we jump to the automotive driving, which is now the boom. Everybody is now trying to catch up. And in this case, you will see here that our system can recognize when he needs to slow speed or change the lane or stop totally, right? So we are also using a similar procedure like we did for the activity recognition. And in this case, we don't have automotive driving, of course, but we have robots. And in this case, our robot is a mobile platform. Then you can see here that this is a traffic light, or simulation of a traffic light. And now the traffic light is yellow, and now it's red. So the robot stops, right? And then he's going to wait until the green happens. And here you can see all the properties that the robot is actually perceiving. And from these properties, this is the behavior that the robot is interpreting. In this moment, he is detecting an obstacle in front, so he's going to slow speed, but now he detects that the obstacle is not moving, he's not going to move, and he has a freeway on the left one, so he's going to just switch to a different lane, right? So in this case, the robot will continue his path, and then what will happen when we have a pedestrian crossing, right? In these cases, we need a system that is fast and is reactive, and then this is was my master's student, Ilya. He's also in the booth if you want to meet him. And he has the very dangerous part of being the pedestrian. And in this case, he trusts totally into his system, so he dares to just cross by. But notice how fast the system recognizes, how fast the reasoner behind is telling the system stop, because you have a human in front and you should not override it. Yeah. Yes, so this is a nice paper that we have also in a conference. And then you tried, I guess you have tried the HoloLens, or you have tried the Oculus or the Vive that are here also in the demonstrations. And we also have our virtual reality system. And what will happen here? Would it be cool that our virtual reality system can understand what I'm actually doing without having to teach him? And this is what we are doing. So in this case, this is a totally new activity because it's washing dishes. If you remember, we only know how to do pancakes and sandwiches. And in this case, we have a task graph. This task graph is actually creating the plan of the steps that the human is performing. And in this case, this that you see here on the lower part is the recognition of the virtual reality system. And this on the higher part is the plan, the graphic plan that the system is recognizing. The nice thing of the virtual reality system is that we can have multiple users and we can have multiple information, store it, and then have a higher representation to interpret all these different behaviors from humans. The nice thing of this is that we just tell the participants using the Vive, now you're going to do the dishes. And some people, for some reason, they decided to clean the whole kitchen. Not just doing the dishes, but they decide to clean the whole kitchen. And then that's why we have different varieties here. Because we don't want to restrict the procedures, the orders. We just want people to do normally what they do, right? And this is the goal. The goal is that our robot is going to learn everything from the virtual reality systems and then is going to execute. Actually, this is not really updated because this is another master student that I have, Thomas, and he has managed to actually transfer it to the real robot. So that was a bit old. And yes, so today we are here, our team, Alle Home, and we are going to compete in this International Service Robotics League, which is called RoboCup Home. And in this year, we are bringing our robot, we are bringing our system. And you will wonder, yeah, what is a RoboCup Home? So RoboCup Home is a set of challenges that deal with household environments, so service robots. So imagine that you just tell the robot, okay, can you bring me a cola? So the robot needs to know that to bring you the cola, he needs to go to the kitchen. Then in the kitchen, he needs to go to the fridge and then fetch the cola, right? And all these procedures, we should not program to the robot, but the robot needs to try to infer that, right? And this is what we are trying to do with the students. Also, we have, this is one of the largest competitions, international competitions that exist on service robotics. And it's very, very challenging to just go to the finals. So just the 50% of the teams qualify to the finals. We were lucky enough to qualify, I must say. And this is our first time going, so we are really proud of what we are doing. So you are welcome to come to our booth and try to talk to some of the students. We have, at the end, we have 8 students. We have bachelor students, master students, and only 1 or 2 PhD students. And this is the team. This is the team that is going to Japan this year. And this is everything, all the modules that the students are programming behind. So we have the object manipulation here, navigation, of course. Object recognition is always important. Speech recognition, so you can have a dialogue with the robot. We have learning by demonstration, that's something that similar to the one I showed you before. And we have the reasoning and the knowledge. So everything, as you saw, basically my work is on the reasoning and on the AI part, and this is what we are focusing. This is our strength, basically, our secret weapon. This is some numbers from the international competition, and this is very, there is a lot of disciplines, so it's not just at home, it's also at work, and it's also at disasters, industrial scenarios, etc. If you want to know more about our team, you are welcome to visit our website, or you can also like our Facebook page. We are trying constantly to update how students are doing, or we also have our YouTube channel. You barely see our email address, but I will show you one more time. And of course, we are also looking for sponsors. So if somebody here from the audience wants to support our very enthusiastic team, please drop by our booth. We have a lot of information about this, and we are very happy that TNG will support us. They will be our silver sponsor from this year, and we are really happy about that and thankful about that. Yeah, so you can come to our booth. So to wrap up about this talk today is that I was talking about human activities demonstration, how this can be implemented into our framework, which we call ISHAR, how this can be implemented on different input sensors. I didn't have the time to explain you about the egocentric view, but if you're interested, I can later talk about that a bit later. We have the automotive driving part, and we have applied this into different robots. Right, so the last robot that I'm working on is a Tiago robot, the one we have here, and happily to introduce my team of the Alle Home. And of course, I was not always working alone, so I have a collaboration. We have a strong collaboration with, so my supervisor is Professor Cheng, and I was also working before with Michael Beetz. And we have some collaborations with Japan and with Seoul, and recently with the US. And this is all the team, and I would like to thank them, and also some of my master students. And we have also our project, our European project, which is called Factory in a Day. You can also Google it. It's very, very cool. With this, I would like to end up the talk, and I hope you enjoy it. And please, if you have any questions, just either ask me right now, or you can stop by the booth. We will be there until, I don't know, 6, 7 or so, till the end of the day, I think. And here is the email address of our team. Finally, I can see it here. And this is what we want to achieve. The robot observes, interprets, and executes the activity that he has seen. Thank you very much.
Thank you very much for your talk. We have a couple of minutes for questions, so let's get started.
I don't need this.
Yes, you need, because we want to have it also
okay.
in the...
So you talked about ontologies, and
Yes.
that your reasoning is based on ontologies.
Yes.
Are there also techniques which adapt the ontologies based on what you newly learned? Because you showed us that
Yes.
somehow you can... that it will ask you, so what kind of activity
Right.
was that? And then it will learn somehow that how the world looks like
Exactly,
automatically?
yes. So that's something it was not shown on the video of the virtual reality, and that's one of the things we're exploiting. That, for example, when he sees doing the dishes, he observes that you are doing the dishes with a sponge, and maybe you start learning with a plate, right? But then you have also a fork. So the system will say that the plate and the fork belong to the same subclass, and then the system will say, okay, washing dishes is for all food utensils, for example, no? Or food containers, for example. So we're trying to actually also teach the system to be general, and if something is not on the ontology, right now we don't have it, but we are working on that, how to include the new knowledge. For example, he doesn't know chairs, right? Where in the ontology we need to place the chair? And that is a very interesting question and a very, very, very complicated research area, and we are still working on that. For example, yeah, where will you classify chairs? In, I don't know, furniture, right? But then you see how much time it took you also to think about the subclass of this activity. But yeah, this is our approach that we take, yes.
Hi. Another question. You showed us how the slicing of bread was shown.
Mm-hmm.
it's hard to get how the robot can actually infer how it is done. I mean, for instance, you need to make sure that you don't cut your own fingers, so you have to move them in a very particular way, in such a way that you don't cut your fingers, but still you're close enough so you can actually handle the bread.
Yes.
How does this come into the ontology, that it recognizes these parts? Do you have to explicitly teach those parts, or can it somehow infer that?
In this case, for example, we have two different problems. So the first problem is the observation and the interpretation, and the second problem is the execution side. So for the execution side, there are different techniques like DMPs and all these programming by demonstration techniques that you actually teach the robot a trajectory, and the robot optimizes to the best, depending, of course, on the embodiment of the robot. Because the ICOP robot will be different kinematics from the Heinz robot, right? And in that case, you have to continue learning. But in the recognition side, you can actually generalize. Of course, right now we cannot get as very specific as you were mentioning, because we wanted to get as general as possible. But we are also trying to explore these new trends of how much force do you need, for example, to open a bottle? How many degrees do you have to pour the bottle? This depends on how heavy the object is, right? How much viscosity the dough from the pancake has. So there are so many different open questions that hopefully everything is not solved. So we still have some job to do. But this is very, very important. I do agree. But right now, our ontology will store general information, not these specific details. Yes.
You showed the tree, which was quite simple for this one task, but
Right.
it can get very complex. Let's say for the dishwashing, if you put for the robot a dirty shoe and a clean and then a dirty fork, how would the system know which one to clean? And the shoe is not to be put into the water, but treated in a different way. So you have to put together maybe, I don't know, hundreds of different simple decision diagrams. How do you train this to be flexible? Because you cannot train any combination of activities.
Yes.
And what is the semantics to combine them, let's say autonomously?
Yes. So right now, the video for also doing the dishes is exactly the same tree. But what is different is how the relationships inside the ontology works. Like I was explaining, so you have the taking. Taking is just with some object. This could be a plate, this could be a fork, this could be whatever. But the main thing that is the reasoning doing is that I have something. And this something is already labeled in our ontology in a really, really high class, so that we can classify as many objects as possible, right? So coming back to your question, then yes. So it's very complicated to know. Also, there are some objects that belongs to different classes, right? Because they could also be relationship between them. So we are also trying to define which object is the optimal for that activity, like I was explaining in the dishwashing. So you may teach with a fork and a plate, but then you have a pot, which you can also clean, right? And then you are also doing with the sponge. But then you have this, when you put it on the dishwasher, you have this, I don't remember this sponge, but it's not a sponge, it's like a brush, exactly, thank you. So, and then this brush is part of the cleaning utensils, right? So then instead of just putting sponge as the classifier, as the class, then you go higher to see how many objects can you cluster for the same activity. Is that more or less?
But the same object can, let's say, be represented in different other tasks.
Yes, of course. Yes.
So then it's complicated.
Yes.
Or the context of
Yes.
the object.
Exactly. So we are actually also working on the context, because if you are in the kitchen, it's a different dynamics that you have. But if you are in living room, for example, the chair has a different functionality than in the kitchen, right? Or more or less, different objects, different functionalities. And also in the automotive driving, for example, when you are in the Autobahn, you have to be careful about different things than when you are in the city center, and then you have to look for pedestrian, dogs, balls, kids, etc. And that is the contextual information that we can also add on top of this. Not done yet, but we're going there. Yes. Yes.
It seems that you have a large number of objects that need to classify. Is there any open source library with properties and with the semantics integrated in a standard way so that you and the other competitors in this competition can reuse existing semantics or existing descriptions or maybe even existing simulations of the object? Because it seems if you don't combine this knowledge in a standardized way, it's a total waste of man hours.
Yes, that's totally right. And then the community has realized about this problem because also we have to compare to each other. And there is no like a benchmark of comparisons. And we're also organizing a workshop in another conference to actually try to put them together, how everything is correctly standardized, right? And the nice thing of the competition is that everything that we do, we're going to release. So for example, right now you can find in our website our Git repository, and in there you can find all the code that the students did for the challenge video. So in there you will find our ontology, you will find our reasoner system, our objects we did, of course, and also one of the challenges of this competition is that there will be some objects that we don't know which one are. And that's very challenging because maybe they will give you a different Japanese bottle. and that is a different thing that we cannot train. But yeah, the idea is to share the data. Yes.
Any more questions?
How do you prevent that it drinks your beer?
Sorry?
How do you prevent that the robot drinks your beer? Do you never show him people that drink
no,
beer?
I haven't. Yeah. I haven't. Yeah. It's there because it's my motivation. So this is what I want to do at the end of the day. So this is actually that something that this robot, the iCup, cannot do because this robot has only a 200-gram payload. So the beer is actually heavier. Or it has to be an empty bottle, which it doesn't make sense, right? So, but with the new robot that we have, the Tiago, we can actually grasp higher objects and heavier objects. So you can ask our students. They are always trying to, oh, Tiago, bring me my Spezi, because they always have Spezi in the lab.
Okay, if there are no more questions, thank you for this exciting talk.
Thank you very much.